Hey everyone. Now we're going to continue our conversation of how to visualize logistic regression results by adding additional predictors to our model. So in the previous videos, we just looked at a simple bivariate model with one predictor and one outcome measure. And now we're going to extend that model and think about different ways of how to visualize results involving multiple inputs, involving multiple predictors, essentially. Okay. So we're going to extend the basic model that we used in the previous set of videos, where we just looked at predictors of Republican support for the Republican candidate in the 2000 U.S. presidential election, and we just looked at the association between ideology, or this ideological feeling thermometer, and the vote choice for the Republican candidate in the election for George W. Bush. Okay, and now we want to control for party identification. Okay, so we want to examine kind of or we want to predict Republican vote share, not only by including ideology but also by including party identification. Right, and so obviously we can't give any of this like a causal identification, but for the purpose of prediction, we might be interested in including both of those as like potentially powerful predictors of turnout and vote choice in particular. Okay. So in order to specify our model, we just extend the formula specification by adding a second predictor, party ID 7. This is as the name suggests, a 7-point party identification scale from strongly Democrat to strongly Republican. And we're just going to treat this as quasi-continuous. If we wanted to take into account potential nonlinearities, we might consider individual dummies for Democrat or Republican identifiers, or we might consider like a square term and so on. But just for the purpose of interpreting regression coefficients and logistic regression coefficients and visualizing, we'll just keep it at this very simplified example. Okay. Obviously, we would also consider additional control variables, sociodemographics, education, and so on, if we really wanted to predict a vote choice, but again, we'll keep the model specification fairly simple and just focus on interpreting those coefficients in a comparative sense, and also visualizing these results. Okay, we can directly. One thing we're going to do is we're going to save the coefficients in a vector called that we would just call B for beta coefficients. We're just going to use that later on to directly basically compute some results to interpret our coefficients better in a probabilistic sense. Okay, so if we look at the output, again, this is similar to the previous result. We have our intercept, which is minus 8.55, which we again cannot directly interpret because this is basically the on this underlying latent scale of this linear predictor. We cannot directly interpret it as probability or on the probability scale. Okay, and we're going to talk in a second about how we can convert that intercept into a probability to actually interpret it. Okay, same goes for the two coefficients for the ideological feeling thermometer. Again, we have a positive coefficient. And remember that this feeling thermometer was measured on a 0 to 100 scale, okay? So a 1 unit increase is a fairly small increase in conservative identification. And just looking at the direction of this association, we can say if we compare respondents who identify or who provided a more warm feeling towards conservatives, we're more likely to vote for the Republican candidate, which obviously is plausible, makes a lot of sense, right? Same for party identification, although here the effect or the coefficient itself seems a lot larger, right? But we have to take into account the underlying scaling of the variable. Party identification is just scaled on a 1 through 7 scale. So 1 unit increase in that variable is much more substantial than a 1 unit increase in the feeling thermometer. Okay, again, we can interpret this in terms of comparisons. If we increase, or if we compare two respondents who differ by 1 unit in their party identification in this particular scale, then we predict, our model predicts that the probability of that respondent with a higher party identification value is more likely to vote for the Republican candidate. Okay, so this is interpreting just the direction of these coefficients, but of course we want to get an additional kind of idea about the substantive effect size in terms of probabilities. Okay, and we talked about a couple of those rules in order to kind of evaluate these coefficients directly on the probability scale. Okay, if we want to compute kind of the baseline probability that is associated with kind of the constant terms, so basically the predicted probability if all predictors are equal to 0, what we have to do is we have to take our intercept and we have to plug it into our link function, which in our case is, of course, the logit link or the inverse logit. Okay, so if we take our inverse logit function and plug in our intercept, we get a probability of 0.00019, so it's almost 0. Okay, why is this probability so small? Remember, the intercept is always interpreted, just like in the linear model, as the predicted probability or the expected value for when all predictors that are included in the model are equal to 0. Okay, and so obviously this is kind of a prediction that is at the end of the spectrum of the variables that we can actually observe. Remember that the feeling thermometer ranges from 0 to 100, so this is basically extremely liberal. And party ID actually ranges only from 1 through 7, so this is even an extrapolation outside of the range of party identification that we actually observe, right? So essentially that means that this intercept itself, by itself, is not directly, doesn't really have a clear, meaningful substantive interpretation. Okay, so how can we get around that? Well, either we can mean center our predictors so that the intercept directly has a more meaningful interpretation, or we can take into account our coefficients for each of those predictors and plug in an average value or any other meaningful value in order to compute this predicted probability for a range of data or for a specific case that is more realistic. Okay, so in our case here, we could compute the average or the median for our feeling thermometer as well as for our party identification. But what I do instead is I just plug in basically the central values on the scale. So 50 for the feeling thermometer and 3 for our 7-point party identification scale. Okay. And of course we have to plug all of this again into our link function to actually compute this as a probability. Okay. So we take our intercept plus our coefficient for ideology times 50, which is the center of that scale, plus our coefficient for party identification times 3, which is the center of that scale. Okay, and that gives us a predicted probability when each of those values are, rather than at 0, they are now at 50 and 3 respectively. Okay, and the predicted probability to support the Republican candidate in the 2000 presidential election is then 0.25. Okay, so that's still fairly low, but we have to kind of both look at the look at the actual distributions of those predictors and also potentially include additional covariates, additional predictors to actually get a better prediction for that election. Okay, but based on that model itself, we would basically expect a probability of 0.25 for respondents who are basically at the center of these scales. Okay. Next, we can evaluate the coefficients themselves. Okay, and again, these are basically coefficients on the logit scale, so we cannot directly interpret them as changes in probabilities. We can compute predicted probabilities, and I'm going to show you how to do that in some of the upcoming videos. But if we want to just get a quick sense of the size of these effects, we can use the divide by 4 rule, okay? The divide by 4 rule, as I mentioned, all we have to do is divide the coefficient by 4, and this gives us an approximation of the kind of largest change in probability for 1 unit change in that predictor, okay? So if we divide our coefficient for ideology by 4, we get 0.02. That means basically at the point on the logistic line where the change in probability is maximized, right? So right at the center, around where the probability is around 0.5, right? Around that point, a 1 unit increase in ideology is associated with approximately a 0.02 change in the probability. Or in other words, keep in mind, we're talking about comparisons here. At the center of this scale, if we compare two respondents who differ in ideology by 1 unit, we predict, or our model predicts approximately, that the probability of voting for the Republican candidate is around 0.02 higher for the respondent with the higher level of the ideological feeling thermometer. Okay. We can do the same thing for our coefficient for party identification. Again, all we have to do is divide our coefficient by 4, and we have 0.0277. Okay, and again, this is the maximum predicted change in probability for a comparison between 1 unit changes in party identification. Okay, comparing two respondents who differ in party identification by 1 unit. The model basically predicts a maximum change in probability of 0.277. Okay, and so that's, obviously seems a lot larger than this change for ideology, but again, keep in mind a 1 unit change in party identification is very different from a 1 unit change in ideology given our scaling. So one thing we might consider going forward, if we really want to compare those coefficients, could be to either to standardize both measures to have a standard deviation of 1, or put them both of them on a 0 to 1 scale or something like that, right? Depending on our specific substantive problem. Okay. So, but this already gives us kind of a good idea of the effect sizes and an approximate kind of evaluation of kind of the range of changes in predicted probabilities that we can expect, right? But obviously we need to go a little bit further, and we need to actually explore these changes in probabilities graphically using ggplot and using R, okay? So what are different ways of kind of visualizing model results when we have multiple input values? And one really cool visualization that is discussed in the textbook is basically graphing raw data and, in addition, discrimination lines for different levels of predicted probabilities, right? And here I'm just going to show you how to recreate that plot in using ggplot rather than base R and the functions that are in the textbook itself, right? And in order to understand kind of how we can create this, the idea here is very similar to, if you remember from the last Q&A session that we had, this heat map that I showed you where we had different levels of probabilities for different combinations of two input measures, right? So now we're doing something very similar, except for the fact that we're not computing kind of predicted probabilities for different elements of this heat map grid. What we're doing is we're directly plotting the raw data in a scatter plot with one predictor on the x-axis and one predictor on the y-axis. We're also going to color code whether each of those individual observations actually turned out to be a 0 or a 1, so a Republican vote versus a conservative vote, Republican vote versus a Democratic vote. And then we're going to basically draw discrimination lines that indicate equal probabilities to vote Republican versus to vote Democrat. Okay, and we're going to see that in a second to make that a little bit more clear. The idea is kind of, you could think of it as similar to, if you look at maps where you have kind of different lines that indicate the same height on a level. If you look at a map of a mountain, for example, right, you usually have these lines that indicate a certain level or a certain height level in that map, right? And this discrimination line is basically exactly the same thing, just based on the model. What is basically a line where this probability, the predicted probability based on the model, is constant, okay? And this gives you kind of a sense of how these two predictors that we're including, that both have kind of a positive impact on the probability of observing a one, how they interact or how they kind of reinforce each other, or to what extent there is a trade-off between those two, okay? So in order to compute these discrimination lines, remember that basically our linear predictor, in our case here, beta 0 plus beta 1 x1 plus beta 2 x2 plus epsilon, we observe our data and we have our parameter estimates, beta 0, beta 1, and beta 2, right? If we now want to basically compute these discrimination lines for a scatter plot of x1 and x2 on the x-axis and the y-axis, all we have to do is basically set our desired probability. You know, it could be 50% or 90% or 10%, for example. And then basically solve this equation where we have beta 0, beta 1, and beta 2 known, and we have our desired level, our desired predicted probability, and then solve that for x2. And that equation then is basically a linear equation that we can directly graph in that scatter plot. Okay, and that sounds a little bit abstract. Maybe in the Q&A session we can kind of go through the math if you want. But essentially all we have to do is basically rearrange this equation to compute basically the specification for the discrimination line for a given predicted probability. Okay. In order to do that, the first thing we're going to do is we're going to just create a scatter plot with our ideology feeling thermometer on the x-axis, our party identification on the y-axis, and we're creating, as I mentioned, a color coding for ones and zeros for each of those observations. We're also just adding points, so a basic scatter plot, as I mentioned, but then we're adding three types of AB lines, so basically just a linear, basically just a straight line, and these straight lines, again, according to the model, indicate equal probabilities. For each of those, we basically set different values of p, and then solve for x2 in order to basically compute both the intercept and the slope for that given discrimination line. Okay, we can go through that math, but essentially here we have a discrimination line for p being equal to 0.5. For p being equal to 0.5, the logit of p is equal to 0, so this simplifies quite a bit. For 0.9 and 0.1, we have to include the logit in there in this equation, and this becomes a little bit more complicated, but important for you is basically the resulting plot and what it actually implies and what it actually means in substantive terms. Okay, as I mentioned, on the x-axis we have our feeling thermometer. On the y-axis we have our party identification. We have a color coding. All these dots are red if the respondent did not vote for the Republican candidate, and turquoise or if the respondent did not indicate to vote for the did indicate to vote for the Republican candidate, and we see basically a clear positive relationship or positive association between both ideology and the probability to vote Republican, and party identification and the probability to vote Republican. As you go further up on the y-axis, we see higher proportions of Republican votes, and as we go to the right on the x-axis, we also see higher proportions of Republican votes. And that means we can basically, compute these discrimination lines that indicate equal probabilities for Republican votes. This lower dashed line here indicates 10% probability. This solid line indicates 50% probability, and this upper line indicates 90% probability of voting for the Republican candidate. Okay, so basically what you can see is around this solid line, if we go around here, approximately, in the direct vicinity, in the direct area close to this discrimination line, there should be about an equal number of 0 and 1 observations in our data. Okay, same here for this 10% line. We should have around 10% votes across, close to this line. Going from the upper left to the lower right, we should have around, in expectation, around 10% of ones and 90% of zeros. Okay, so this is a very nice visualization to kind of show the effect or show the association between two independent predictors and their effect on the predicted probability of observing, in our case here, a Republican vote versus a Democrat vote for the Democratic candidate. Okay, so this is just another additional kind of visualization technique to keep in mind if you work with logistic regression and multiple predictors, and you're interested in kind of visualizing how these two predictors kind of work together and impact probabilities kind of in conjunction. Okay, all right. I'm going to take a break here, and in the last video for this section, I'm going to kind of expand this one step further to talk about logistic regression with interactions.